Welcome to another lecture series in AC 311. And today we will cover one of the major content of the course, and we are talking about chapter 2. We are moving from prerequisite courses to chapter 2, which is electrostatics. Okay, and in this video we'll cover Coulomb's law and electric field. So here is the fundamental problem that we are trying to solve in electrodynamics. Suppose we have bunch of charges Q1, Q2, let's say we got more all the way through Q n, and we are trying to, so all these source charges, all these charges collectively over here are called source charges, and we are trying to determine what is the force exerted by these source charges on some test charge Q. Well, for this we will have to find the force exerted on Q, on capital Q, due to individual charge Q1. Let's say that is force F1, and electric forces are vector, so we'll just use a vector notation. And then next is we again have to determine the force exerted on Q, capital Q, due to Q2, F2, and we will carry these process all up to the nth charge, and finally the total force will be the superposition of all these electric forces, that is F1. This is not an ordinary summation, rather a vector sum. Okay, however in electrodynamics the source charges itself are moving. And that makes things complicated, because the force now not only depends on simply the position, but also on velocity and acceleration of the source charges. And calculating this is not straightforward. Therefore, we begin with the simplest case, where all our sources charges are static. So, however, our test charge can still move. So, electrostatics itself means we are trying to calculate the effect of static source charges on test charge, which can either be static or the test charge has a moment of freedom, but not the source charges again. Let us begin with simplest case. That is, what is the force on a test charge Q due to a single point charge Q? Let's say we have a single point charge Q, and then we are trying to calculate what is the force exerted by this by small q on capital Q. This force is given by something called Coulomb's law. This is a fundamental law, and this was published in 1785 by Charles D. Coulomb. A French scientist, and we'll talk about a lot of French scientists, and rightly so, because they have an immense contribution in electromagnetics. So this Coulomb's law states that the force between two charges is is directly proportional to the product of two charges and inversely proportional to the square of the distance between the charges. Let's say the distance between the two charges is r, and we also, since we broke this constant of proportionality into an equation form, we also need a constant k. Okay, once again, Coulomb's law states that the force between two charges is proportional, let me write that down, proportional to product of charges and inversely proportional to the square of distance between them. And in okay, we'll just put k over there, but we forgot something. This f is a vector, so we also need a unit vector that points from source to the test charge. So for now I'll just call it ar hat. Okay, that is our Coulomb's law. And in SI unit, this k is 1 divided by 4 pi epsilon 0, which brings us which equates f as 1 divided by 4 pi epsilon 0 q times q divided by r square ar hat. Okay, this is the simplest form of Coulomb's law for 2-point charges. And often in electromagnetics, we assume the source charge is at a position r prime and test charge is at r, then our capital R in vector form is r minus r prime, which enables us to write Coulomb's law as F equals to, this is constant, small q times capital Q divided by, now R is r minus r prime, where r and r prime both are position vector, and I'll also write this ar hat in terms of its vector constituent, which is r minus r prime divided by the magnitude of r minus r prime. That is the definition of unit vector. Okay, so this is the force between two charges, small q and capital Q. Okay, so let's move on to a different way to express Coulomb's law. And okay, let me write this chapter. We will be discussing about electric field in this subtopic. So now the question is, okay, how is, so we told over here Q is at some point and the capital Q, the test charge, is at a different point. So now the question is, how is Q able to exert force on Q because there is some distance between Q and capital Q and small q, and the question is, how is small q able to exert force on capital Q? Okay, and this we still don't have a concrete answer to this question, but the solution proposed by field theory is a charge, if you have a charge q, then it exerts something called electric field around it. Okay, or in other word, if I were to represent this electric field, I use a arrow, and as you go far away, the strength of the electric field decreases. Okay, and that happens in all direction. Okay, so field theory states that a charge exerts electric field around itself, and if another charge is within this electric field, that test charge experience a force. In other words, what the field is doing is it's essentially transmitting the influence of source charge on some test charge q. Therefore, the goal in this course is to learn theory of field rather than the study of forces. Okay, and to understand the field, let us rewrite Coulomb's law in a different form. So let me start with F equals to 1 divided by 4 pi epsilon 0 q times q divided by r square a r hat. But now I'll just say F divided by q, where q is test charge, is equals to 1 by 4 pi epsilon 0 q over r square a r hat. Okay, this quantity on this side, so this is force per unit charge, and this is defined as electric field represented by E with an arrow, because that is a vector. So in other word, E is 1 divided by 4 pi epsilon 0 q divided by r square a r hat. So this is the electric field of source charge. Electric field due to source charge small q. And as you can see, this electric field is a function of r, and therefore it depends on the position you are at. So if you calculate your electric field at this point, it will be stronger, and as you move away from your charge, your electric field strength decreases. And notice that this electric field has no reference to the test charge q, because here we have isolated the source of field from the object placed in the field. Okay, I'll explain more in a detail. Okay, so this is electric field due to a single point charge q. If you have multiple source charges, E will be 1 by 4 pi epsilon 0. So I'm considering something like this, where we have something like this, where we have multiple source charges at a stationary point. 1 by 4 pi epsilon 0, and due to q1, that is q1 divided by r1 square times unit vector ar1 plus q2 divided by r2 square times ar2, and so on. And combining this, into a shorthand form, we still have 1 by 4 pi epsilon 0, and this will be summation I equals to 1 to n qi divided by ri square times ari hat. Okay, this is the electric field due to multiple source point charges. Okay, now let us explain a little more about the electric field. So electric field is a vector quantity that varies from point to point, and it depends on the configuration of source charge. Let me write that down. So E is of course a vector that varies from point to point, and it also depends on the configuration of source charges. And as we defined earlier, E is force per unit charge, that would be exerted on test charge if a test charge was placed at P. So what I mean by this is, so like I told, let us take a simple configuration, something like that, or we can take more charges. Okay, we have charges. If you placed a test charge Q over here, so we are asking, okay, what is the electric field vector over there? And that electric field vector at that point is, let's say this is point P1. At point P1 is the force per unit charge that is exerted on that test charge Q when it is placed at point P1. So when it is placed as a different point, let's say P2, now a lot of things has varied. The position of the point has varied, even though the source, even though the test charge, even though the test charge is the same, your electric field vector at this point P2 would be different. If you place the same source charge at a different point at P3, again your electric field would vary at that point. So electric field vector is a function of position. And as you go away from the source charges, it decreases because you have 1 by r square term over there in the denominator. Okay, and here is some important conceptual ideas. So you can think the concept of the electric field to be similar to Earth gravitational field. Near the surface of the Earth, right? So near the surface of the Earth, the G value is 9.8 Newton per kg. And that means that if you place 1 kilogram mass over there at that location at the surface of the Earth, then that experiences a force of 9.8 Newton. Okay, so what you essentially did over here is, instead of calculating gravitational force using Newton's law of gravitation, F equals to G m1 m2 divided by r square. You simply computed what is the gravitational field at a given point, and now you can place any amount of any mass over there at that point, and you would get the force on that mass. So instead of calculating gravitational force using Newton's law of gravitation every time a new object is placed at the surface, we can simply define the region by its gravitational field G. Okay, so the field concept is almost the same. What we do is we determine what is the electric field produced by a given configuration of source charges, and once you get that, no matter if you can have a knowledge of field. Okay, so the field strength E at this point is some, let's say this is point P4. If you know the electric field at point P4, then okay, at P4, if your E is known, now you can simply calculate your force as Q times E. Okay, let's say this is P4, this is P4. Okay, so for any test charge, whether your test charge is 1 Coulomb or 2 Coulomb, or it can be anything, usually test charges are not that big, let's say whether your test charge is 1 nanocoulomb or 2 nanocoulomb or whatever, if you have knowledge of what is the electric field at point P sub 4, then you can easily calculate the force on your charge. And this actually, so I'm not writing, I did not invent this formula. This comes from here, from the definition of, okay, from here the definition of E. Okay, I hope that helps. The idea of field is separating. Okay, so this is separating source of field from object in the field. Just for an example, source of field is your stationary charges and your object in field is your test charge. That's all for this, and I'll see you in the other one.